Hi, and welcome to a brief introduction to logic gates. We'll be doing this more in class, but I need you to have just a source that you can come to if you're a bit confused. Okay, this is actually an abridged version of a longer video. If you want to have a look at that video, I do suggest you do this. Big thank you and shout out to that video. Okay, so these are transistors. We've been talking about them in class. This is a lovely image that shows you how they've changed over time. That 1941 one is quite big. I think from memory it's about the size of my hand. So we've gone from the size of our hand down to something quite small. And so that becomes important for what we're doing next, because logic gates are simply lots of transistors put together in combination to create a command of its own. So you can see here in this image, there's not, XOR, NOR, NAND, and OR. And that means they can feed data through those gates instead of just one transistor, and that will actually do a full command in that regard. And it's how our computers actually work, by combining transistors and logic gates, and this is how computers physically work. So how do they work? Well, you can create a gate that says not. So what that means, if it's a 0, you put it through a logic gate and it will become a 1 because it's not 0. So alternatively, as you can see from the table here, if it was a 1 that was put in, the output would be 0. So that's a not gate. Then this one, we've got two inputs, input A and input B. So if input A is 1 and input B is 0, and then we go through an AND gate, we get a 0. Now the reason why we get a 0 is because they're not both 1. You can see here from our table down here, if they're both 1, the output becomes 1. In any other circumstance, it becomes 0. This becomes important later on, and it's going to be important for an activity we're doing in class. Okay, so it's possible to combine gates as well. So here, when we add them together, we've got our NOT gate, we've got our AND gate, and so now we put it through an AND gate and then a NOT gate, and we get 1, and you can see how there are different variations on that. And again, here's your output table. This might be a bit confusing, but what I'm trying to show you is that by putting various inputs in through these logic gates, it means that our coding can be understood by the computer in a more complex manner. So when we put a NOT and an AND gate together, it's called a NAND gate. And so this is now what it comes up with. This is just an example. So what I'm trying to show you is that there's not just two gates, there's a range of gates. This next slide is examples of the gates that you can have. So these are all different types of logic gates and result in different outcomes. So as you can see here, the various inputs will end up with different outcomes. And this is how computers physically work on the inside. This is a diagram. So you can see here we have 4 inputs on the left-hand side, A, B, C, D, and we can get to different outputs on the other side, but we get 9 variations, depending on what logic gate we go through. I know this looks complicated, but it's much more simple than having it as a range of transistors. Please note that the source for this image is not from the video that I recommended earlier. So now that we've had an introduction to logic gates, we're going to be doing an activity in class which will hopefully clarify all this for you. If you didn't get to do that class, I hope this video has been a basic introduction. You don't need to understand the complexities, I just need you to understand that logic gates exist, that it's combined transistors giving a command of its own, and by putting logic gates together in a sequence, we can get different outcomes, different outputs from our inputs. And this is what physically makes computers work.